Welcome back to another Orange Coast College mathematics video. In this video, we're going to be talking about the inverse trigonometric functions. Now, we have some of the graphs of them here, and we'll talk about that in a second, but I want to explain a key point for this. And we know what inverse functions are. You switch inputs and outputs. But many, in fact, all of these trigonometric functions are not invertible on their entire domain. What I mean by this is think about the function y equals x squared, and it's sort of inverse y equals the square root of x. If I ask you x squared is equal to 4, how many values of x makes this true? Well, x can be 2 or negative 2. There are two values that are the answer to this. However, when I ask you what the square root of 4 is, we say it's just 2. This is why they're not true inverses. For y equals x squared, there are two inputs that give you 4, but the square root of 4 is only 2. And we do this to make the radical function a function. If we said radical 4 equals plus or minus 2, it wouldn't be a function because we would be getting two outputs. And we're going to need to do the same thing for the inverse trig function, which is why when you look at this sine function, for example, we are only looking at it from negative pi over 2 to pi over 2. So that when you invert it, we see that the range for sine inverse is only going to be from negative pi over 2 to pi over 2. It's not going to be from anywhere else. We call this the sine inverse function or the arc sine function. Arc sine is kind of nice because sine inverse of x could make you think, oh, that's the same thing as 1 over sine of x, but it's not. Sine inverse is referring to the inverse of a function switching inputs and outputs. And we do the same thing for cosine here. Cosine is going to go from 0 to pi for its inverse. The range of cosine inverse is from 0 to pi. And for tangent, it's going to go from tangent, we actually, since it shoots off to infinity to negative infinity, its domain is all real numbers, but its range is from negative pi over 2 to pi over 2, just like sine, although we are not including the pi over 4 and the negative pi over 4. And then we've got similar graphs for the inverses of the other three trig functions. So let's go ahead and see how some examples of this work actually in practice. In this first problem, I'm asking you what the sine inverse of negative radical 3 over 2 is, which means I'm really asking you to find the angle that gives me the trig value negative radical 3 over 2. Well, we saw up top that sine inverse is going to be restricted from being from negative pi over 2 to pi over 2, just the first and fourth quadrant in the unit circle. I also know that I'm saying, really, when is the sine of this theta going to give me negative radical 3 over 2? Because it's a negative value, I know I'm going to be down here in the fourth quadrant. And when does that happen? Well, filling in my special right triangle, that's when sine is opposite negative radical 3, hypotenuse 2. That means the adjacent is 1. But the point is, when does this happen? Well, this is a 30, 60, 90 triangle when the angle here is the 60-degree angle. So we're talking about negative 60 degrees, or in radians, negative pi over 3. And you have to say specifically negative pi over 3. You can't say, oh, 5 pi over 3 and just go all the way around here. That would give you the same sine value, but again, we are restricting our range to only get one answer. That way it's a function, just like we restricted the square root of 4 here to only give us 2. All right, so let's go ahead and try another one. Here we're saying, when is the secant of theta negative radical 2? Well, that's the same thing as saying the cosine of theta is negative 1 over radical 2 because it's the reciprocal. And if I rationalize that, I get cosine of theta is equal to negative root 2 over 2. Oh, and when does that happen? Well, cosine, we said, or cosine inverse rather, we're restricting to between 0 and pi in the first two quadrants, and it's getting negative, so it's over here. And of course, we know from the unit circle that cosine of theta being radical 2 over 2 happens at 45-degree angles or pi over 4 angles. Since we're in the second quadrant, this is going to be 3 pi over 4. And in this next problem, this is interesting because we're taking the sine of the tangent inverse of negative 2/3. And you might have initially asked yourself, wait, negative 2/3, that's not one of our special ratios. I'm not going to be able to just pull that from the unit circle. However, because we're taking the sine of the tangent inverse, we're going to be able to work our way through this. So let's start with just the tangent inverse of negative 2/3 is going to be equal to some theta value that we're going to try and find. Well, tangent inverse is only defined in the first and fourth quadrant, and it's negative, so we're down here. The tangent inverse of that angle is going to be opposite negative 2 over adjacent 3. The negative 2 is the negative 1 because it's going down in the y direction. Using the Pythagorean theorem, I can get that negative 2 squared plus 3 squared needs to be r squared. So that's 13 is equal to r squared, or r is radical 13. So this guy here is radical 13. Why is that useful? Well, if I know that the tangent inverse of negative 2/3 is going to be this theta, what am I really asking you for? I'm really asking you to then find the sine of that theta. If tangent inverse gives me an angle, I'm really saying find the sine of that angle. So let's just look at the picture. The sine of this angle is opposite negative 2 over hypotenuse radical 13. And we can just do a quick rationalization of the denominator to make this negative 2 radical 13 over 13. So we were able to find our answer without using a calculator. All right, and this next problem, they're not giving us a specific value. They're just saying the cosecant inverse of u. So really, this is my theta, and I'm trying to find the secant of that theta. Well, theta being equal to the cosecant inverse of u is the same thing as saying the cosecant of theta must be equal to u, or I'm going to say u over 1. Why would I do that? Well, let's sketch a little picture here. If cosecant of theta is equal to u over 1, remember cosecant is hypotenuse u over opposite 1. And then using the Pythagorean theorem, I can find this missing side. U squared should be equal to 1 squared plus the x squared. That means u squared minus 1 equals x squared, or x is equal to plus or minus the square root of u squared minus 1. However, cosecant is only defined in the same places as sine in these first two quadrants, so this is really going to be just the positive square root of u squared minus 1. And so what does that leave us with? Secant of theta, this is the theta here, has to be equal to adjacent, or hypotenuse over adjacent. So that is going to be u over the square root of u squared minus 1. And you can rationalize that if you wish, or leaving it as is perfectly fine as well. Moving forward, we're being asked to find the solutions to these equations. So in this problem, I'm trying to isolate x. Well, let's start by dividing both sides by 9. This is going to be the tangent inverse of x then is equal to 3 pi over 9 is the same thing as pi over 3. Well, that's the same thing as saying x is equal to the tangent of pi over 3. And x is equal to the tangent of pi over 3 when? Well, the tangent of pi over 3, you could look at your unit circle, or you can draw a quick sketch. Pi over 3 looks something like this. My special right triangle. Tangent of that angle is going to be opposite over adjacent, which is radical 3 over 1, or just radical 3. Now in this last problem, this is also interesting. They're saying what is the value of x where the arc sine gives you the same thing as the arc tangent of 3/4. Remember, arctangent and arcsine are just the same thing as tangent inverse and cosine inverse. So they're saying, what do I need to take the arcsine of to get the same thing as the arctangent of 3/4? Well, let's temporarily let theta be equal to the arctangent of 3/4. It's going to be an angle after all. That same angle, theta, is going to be the arc sine of x. Well, this means the tangent of theta should be 3/4. If the tangent of theta is 3/4, we're trying to figure out what the sine of theta is going to be. That will give us the x value that we want. Well, let's sketch a quick picture. The arctangent of 3/4 is going to live here. We've got an opposite of 3 and an adjacent of 4. That's a perfect triangle, 3, 4, 5 triangle. So this hypotenuse is 5. And therefore, we have what? That if I want the sine of that angle, I am really just taking the opposite 3 over hypotenuse 5. And that will be the value of sine of theta. Or I guess I should say the sine of x, since we were using x in this problem. All right, that concludes this video. At this time, if you're ready, you may move on to the next one.